Good morning, students. Let's start a new chapter. Chapter 5th, States of Matter. Now, some important points and terms of the chapter. First, intermolecular forces. Intermolecular forces are the forces of attraction and the repulsion between interacting particles. This term does not include the electrostatic forces that exist between the two oppositely charged ions and the forces that hold atoms of a molecule together. As for example, covalent bond, attractive intermolecular forces. These forces are known as van der Waals forces in honor of Dutch scientist van der Waals. Now, second topic is dipole forces. Dipole forces act between the molecules possessing permanent dipoles, plus and minus. Ends of the dipole possess partial charges, and these charges are shown by Greek letter delta, delta plus and delta minus. Now, example of dipole forces between HCl, H plus and Cl minus. Now, induced dipole forces. This type of attractive forces operate between the polar molecules having permanent dipole in this figure. Delta plus and delta minus are permanent dipole of polar molecules. This type of attractive forces operate between the polar molecules having permanent dipole and the molecules lacking permanent dipole. Permanent dipole of the polar molecules induced dipole on the electrically neutral molecule by deforming its electronic clouds. Thus, an induced dipole is developed in the other molecules. Now, fourth topic is dispersion forces or London forces. Atoms and non-polar molecules are electrically symmetrical and have no dipole moment because their electronic charge cloud is symmetrically distributed. But a dipole may develop momentarily even in such atoms and molecules. This can be understood as follows. Suppose we have two atoms A and B in the close of each other. It may so happen that momentarily electronic charges distribution in one of the atom, say A, becomes unsymmetrical, means the charge cloud is more on one side than the other. This results in the development of instantaneous dipole on the atom A for a very short time. This instantaneous or transient dipole exerts the electron density of the other atom B, which is close to it, and as a consequence, a dipole is induced in the atom B. The temporary dipoles of atom A and B attract each other. Similarly, temporary dipoles are induced in molecules also. This force of attraction was first proposed by German physicist Fritz London, and for this reason, force of attraction between two temporary dipoles is known as London force. Another name for this force is dispersion force. Now, fifth topic is hydrogen bond. Hydrogen bond is represented by a dotted line, while a solid line represents the covalent bond. Hydrogen bond can be defined as the attractive force which binds hydrogen atoms of one molecule with the electronegative atom, as for example F, O or N. Now, sixth topic, Boyle's law. This law is related to pressure and volume. A constant temperature, at constant temperature, the pressure of a mixed amount of gas varies inverse. Pressure varies inverse to the volume of the gas. At constant temperature, the pressure of fixed amount of gas varies inversely with its volume. This is known as Boyle's law. In this law, according to this law, P varies inversely to volume. So P is equal to K, which is constant, into 1 upon V, means PV is equal to K. K is constant. And P1 V1 is equal to P2 V2, and P1 upon V1 is equal to P2 upon V2. Now, seventh topic of this chapter, Charles' law, which is related to temperature and volume. It states that pressure remaining constant, the volume of a fixed mass of a gas is directly proportional to temperature. Means V varies T. So V is equal to K into T, and K is equal to V upon T. Therefore, V1 upon T1 is equal to V2 upon T2. Now, eighth topic of this chapter, Gay-Lussac's law, which is related to pressure and temperature. This law states that at constant volume, pressure of a fixed amount of a gas varies directly with the temperature. Mathematically, P varies T. So P is equal to K into T, and so K is equal to P upon T. Here K is constant, P is pressure, T is absolute temperature. Now, Avogadro law, ninth topic, which is related to volume and amount. This law states that equal volume of all gases under the same conditions of temperature and pressure contain equal number of molecules. Means V varies in V means volume, whereas N means number of molecules. V varies N means V is equal to K into N. Since volume of a gas is directly proportional to the number of moles, 1 mole of each gas at standard temperature and pressure means STP will have same volume, standard temperature and pressure means 273.15 Kelvin means 0 degrees Celsius. Temperature is 273.15 Kelvin and pressure is 1 bar, which means 10 raised to 5 Pascal. 1 bar means 10 raised to 5 Pascal. Now, 10th topic, ideal gas. A gas that follows Boyle's, Charles and Avogadro law strictly are called ideal gas. Now, ideal gas equation is P into V is equal to N into R into T. Here P is pressure, V is volume, N is number of molecules and R is constant, which is gas constant, and T is absolute temperature. Now, universal gas constant. Universal gas constant, which is expressed as R, and value of R is 8.314 into 10 raised to minus 2 bar length Kelvin per Kelvin and per mole. Universal gas constant R is called gas constant. It is same for all gases, and value of R is equal to 8.314 Pascal meter cube per Kelvin per mole, which is equal to 8.314 into 10 raised to minus 2 bar L K power minus 1 mole power minus 1, which is equal to 8.314 Joule K power minus 1 M power minus 1. This is universal gas constant R and its value. Equation of state. Equation of state is P1 V1 upon T1 is equal to P2 V2 upon T2. Now, density and molar mass of a gaseous substance means N is equal to dRT upon M or dRT upon P. Now, Dalton's law of partial pressure. This law states that the total pressure exerted by the mixture of non-reactive gases is equal to the sum of the partial pressure of individual gases. Means the pressure which these gases would exert if they were enclosed separately in the same volume and under the same conditions of temperature. In a mixture of gases, the pressure exerted by the individual gas is called partial pressure. Mathematically, we can show that P is equal to P1 plus P2 plus P3 plus so on, where P total is the total pressure exerted by the mixture of gases, and P1, P2, P3 etc. are partial pressures of gases. Now, 16 topic, kinetic molecular theory of gases. Gases consist of large number of identical particles, which are atoms or molecules, that are so small and so far apart on the average that the actual volume of the molecule is negligible in comparison to the empty space between them. They are considered as point masses. This assumption explains the great compressibility of gases. Explain the great compressibility of gases. There is no force of attraction between the particles of a gas at ordinary temperature and ordinary pressure. The support for this assumption comes from the fact that gases expand and occupy all the space available to them. Particles of a gas are always in constant and random motion. If the particles were at rest and occupied fixed positions, then a gas would have had a fixed shape which is not observed. Now, next topics will next time. Till then, goodbye.